technology areas that are so critical, we want to go ahead and cover them now as we wrap up Module 2. We want to cover them before we hit the other modules of this course because they do have implications, they do have impact for all of the other technologies that we are going to discuss in this course. Let's talk about high availability in our designs here in this lesson, and then we'll wrap up Module 2 in the next lesson by talking about designing network management into all of the network models that you create. You know, it is often the case that we design some level of high availability solutions into any network model that we want to propose. If you look at this sample model that I've got on screen, you can see that there is a lot of redundancy built in it, isn't there? We can see it looks like the access layer here has multiple options for accessing the network. It looks like there's redundant connections, and there are, to redundant devices in the distribution layer. And then it looks like the core layer has some redundancy in it as well. So we typically have redundancy in our designs. It's really, as I said earlier in the course, a function of budget and a function of just how mission critical a particular service or application is to the business goals of the organization. I'll tell you, when I teach these classes for you, I am engaging in some pretty decent redundancy. I am teaching from a small office, home office, but I am featuring redundant routers with redundant connections to multiple ISPs. I happen to be broadcasting from Tampa, Florida, by the way, the lightning capital of the world. So it's pretty important that I have these layers of redundancy for this mission critical for me educational traffic that I'm sending out there on the internet. How much redundancy you have, again, will be a function of those two parameters, and there's a lot of different redundancy options that you can utilize in your networks today. One of the things that we're going to focus on is workstation to router redundancy, and this would, of course, be at the access layer. Now, it's very, very important that your devices can maintain their default gateway information. We said in networks today, it's more of like a 20-80 model, where 80% of what they want to reach is going to be through a default gateway. So it's pretty darn important that we make our default gateway available, right? All the time. We'll take a look at server redundancy. Sure, we often feature server redundancy in our server farms. We'll talk about route redundancy and even media redundancy at the access layer. But by far, the biggest topic here for us to discuss is workstation to router redundancy. There is a terrible, terrible way to implement this, really, and that is to rely on what's called proxy ARP. This is where a workstation wants to communicate with some remote host, so it ARPs. It doesn't have a default gateway configured. Okay, so there's no default gateway configured. Silly. But so anyways, it ARPs for the address of the host, and the router hears this, realizes that it can service that request, and responds like it's the client using proxy ARP to the device. So here is the router responding on behalf of the client. Okay? Saying, oh, yeah, I hear your ARP. I know I can get you to that particular host, so I'll pretend I'm the client, and now the workstation will send the traffic to the router. What is the most common way to build in the workstation to router redundancy, but not the best way, is a lot of operating systems allow a default gateway configured, and then another default gateway configured, and then another default gateway configured. This explicit configuration of multiple default gateways. The problem with this is, right off the bat, latency. there's going to be this latency while the device figures out default gateway 1 is dead, and then, it'll cut over to default gateway 2, maybe that one's dead, so more latency as it cuts over to the third configured default gateway. So not the prettiest of solutions. The other problem with this is not all operating systems support the configuration of multiple default gateways. We want a solution that can be used without fail by every single host in our infrastructure. We also want to take the burden off the hosts. You see, routers, some of them, can run the ICMP Router Discovery Protocol. Some routers and some hosts can run this. If the routers and the hosts can run this, this is another protocol that allows hosts to dynamically discover an available default gateway. Yeah. But again, we have to make sure the routers and the hosts support this technology. And again, we're placing a burden on the host. It's just like the routing information protocol. Sure, some hosts can run RIP, and therefore they could dynamically discover a default gateway utilizing RIP. But again, this places a burden on the hosts, and we got to make sure all of our hosts support RIP if this is going to be our workstation to router redundancy solution. What is preferred is a solution that doesn't place any burden on the hosts and that is completely transparent to them. All they need to do is configure a single default gateway and magically have the redundancy. These three protocols are called first hop redundancy protocols. That's what we would call these generically. And they are hot standby router protocol, the virtual router redundancy protocol, and the gateway load balancing protocol. HSRP, VRRP, and GLBP. HSRP was a Cisco invention years and years ago, and the IEEE, the standards body, said, you know what, that is a great idea, and they created their own open standard version of HSRP called the Virtual Router Redundancy Protocol. So HSRP and VRRP are practically identical. It's just one is Cisco proprietary and the other is an open standard. The latest, greatest technology, though, an invention from Cisco, is Gateway Load Balancing Protocol. This is the most sophisticated of the first hop redundancy protocols. Let's go ahead and make sure you understand each one of these technologies. So let's spend some time on HSRP. We'll spend time on our VRRP and our GLBP and make sure you completely understand them. With the HSRP protocol, let's say we have a couple of multi-layer switches. This is switch 1, a multi-layer switch. This is switch 2. These feed into, well, typically a layer 2 switch. And then that's going to feed out to client workstations. Okay. On switch 1 is a potential default gateway address. Let's say it's 10.10.10.1. And on switch 2 is a potential default gateway address. Let's say it's 10.10.10.2. Here's what we go out and configure for default gateways on the clients, however. And now you're looking at this and you're saying, Anthony, what have you done here? You've gone out and for a default gateway assignment on those hosts, you've given them a default gateway assignment that doesn't exist on any of the devices in your infrastructure. What in the world is going on here? Well, here's what's going on. These two multi-layer switches, they are configured in what we call an HSRP group. And they present to the clients a virtual default gateway address of 10.10.10.5. 3. This address, notice, actually isn't assigned on either of the multi-layer switches. This address is not assigned on either of our multi-layer switches, but it is what they're configured to send traffic to. Now, one of the HSRP devices, let's say it's switch 1, is called the active device, and it's the one that's actually forwarding traffic for the 10.10.10.3 virtual address, and switch 2, therefore, would be our standby HSRP system. These two switches exchange HSRP messages with each other, and they're checking on each other's health status. For instance, if switch 2 no longer hears from switch 1, it realizes that switch 1 has died, and it will take over as the active device. So suddenly switch 2 becomes active, switch 1 goes into the standby mode, and notice how wonderful this is. These devices are transparently providing access for these clients as they are transparently serving up this virtual default gateway address for the clients. What is really cool about this is once you master this technology of HSRP, you'll have very little problems understanding and mastering the designs for VRRP. VRRP works about the same way. Remember, this is the open standards version of HSRP, and it's called the Virtual Router Redundancy Protocol. We have our two nodes. This is switch 1 and this is switch 2. And they are configured in what's called a VRRP group. And this is called the master device, the one that's actually doing the forwarding, and this is called a slave device. And they present a virtual default gateway address out to the clients. Now, one thing that's interesting about VRRP is that you can utilize the same address that's on the master device. So notice the virtual address in this case is the actual IP address that's on switch 1, and then there's a unique different address on switch 2, but the failover works just the same. So one subtle difference with VRRP is it is not a separate address that is used for the virtual default gateway. The other difference is, notice they use this master-slave syntax instead of active and standby. But the most unique of the first hop redundancy protocols is Gateway Load Balancing Protocol. With Gateway Load Balancing Protocol, as its name implies, we not only have the ability to do the redundancy, but we also have the ability to do load balancing. It's a lot easier to use a lot more devices. Let's say we have switch 1, switch 2, and switch 3. They will be configured in what's called, surprise, surprise, a GLBP group. Okay, so this will be a GLBP group. And sure enough, there'll be this virtual default gateway address that is handed out to your clients. Now, what happens is there's one of the devices, let's say it's switch 1, which is elected as what's called the active virtual gateway. And then you have active virtual forwarders. And by the way, the active virtual gateway can function also as an active virtual forwarder. Now, what happens is when the host ARPs for the 10.10.10.3 MAC address, the active virtual gateway responds to ARP requests, and it can round robin with the virtual MAC addresses of these different machines. How clever. So switch 1 can respond to the first ARP it receives with its own virtual MAC address. Then it can respond to the second ARP it receives with switch 2's virtual MAC address. And then it can respond with switch 3's virtual MAC address. So it can round robin the traffic over the available active virtual forwarders. If you don't like the round robin simplistic load balancing approach, you can configure several other load balancing approaches for the gateway load balancing protocol. So you can see the most sophisticated of all of these first hop redundancy protocols is the gateway load balancing protocol approach, and that's because it can do this clever trick with the address resolution protocol to go ahead and hand out different active virtual forwarder addresses based upon the load balancing mechanism that you configure it with. Another area of redundancy that we want to discuss with you is the area of server-based redundancy that could take place in the server farm or data center. Oftentimes, for key server functions like file sharing or application sharing, we want to mirror multiple servers with each other so that if there was a failure of one server, we can dynamically fail over to another server. In the case of voice over IP, we have this critical device that replaces the traditional PBX, and it's called a call manager. Because it is so critical for routing call traffic, we typically have those in the server farm configured in what we call a cluster. And again, the idea here is if one of the devices is to fail, automatically, transparently, another device starts servicing the voice over IP clients. When we look at our wide area network configurations, for instance, we'll see that we like to configure redundancy between our campus infrastructures. This will allow us with our routing protocols to do load balancing. And also, obviously, it increases availability because if there is a break in one of the paths, Site 1, in this case, and Site 2 can still reach each other by going through another one of the locations. It's wonderful to have this redundancy with your routes to get to destinations, but realize if you're going to do it over a WAN cloud with like a full mesh configuration, like we see in this example, realize that you are going to have the configuration overhead and quite an expense here because you're going to have to create so many circuits. One of the reasons that full meshes aren't that commonly implemented is the fact that there's so many circuits that have to be created. You should memorize this formula for CCDA purposes. It's n times n minus 1 divided by 2. This is the number of circuits you have to create based on the number of nodes. So n is the number of nodes, and again, you'll have to go ahead and configure that many circuits based on the number of nodes that you have. Let's double check that math against the topology we see here. There's 4 nodes, so that would be 4 times 3 divided by 2. So that would be 6 links that we have to create. So 6 links have to be created in this particular case, and it looks like that's right. 1, 2, 3, 4, 5, 6. So we can see the formula works out just perfect, and notice you're going to get a lot of links needed as you add nodes to the environment that you want to connect in a full mesh. Later on in this course, when we start examining your routing protocols, we will be examining the high availability options and the load balancing options for your routes. In other words, EIGRP has specific characteristics and capabilities when it comes to load balancing versus OSPF. It's going to have different capabilities and characteristics when it comes to load balancing. So each of your routing protocols is going to have different capabilities here, and we'll be covering those in detail when we get to the various routing protocols. Media redundancy is something that we do typically have in our infrastructures, and this is where we are connecting devices with multiple paths. Always a great idea, right? If you have a failure of a link, it's always a great idea to have that backup link in place. But at layer 2, we need the spanning tree protocol, don't we? Because if we don't have the spanning tree protocol, we can have loops that occur in layer 2. These will quickly bring the network to its needs. So in a layer 2 infrastructure where we have this media redundancy between our devices, it is spanning tree protocol that is going to come to the rescue. We'll be talking more about spanning tree protocol in our chapter on building the campus LAN infrastructure. In a wide area network environment, we might have floating static routes. Floating static routes are static routes that point to a backup path. Okay? Let me actually show you on a whiteboard how that would work. The floating static route concept. It's important that you understand that, and I find a lot of times students just really do not get the concept of a floating static route whatsoever. All right, what we have with the concept of a floating static route is, let's say we have this New York City location, and there's a WAN circuit out to, typically you always say London, right? So we've got this New York City to London connection. And then there is this slower and, more hops involved connection via Miami. And we want the traffic, obviously, to take this direct connection between New York City and London. So this is the main path. And let's say it is learned via EIGRP, and this has an administrative distance of 90. So EIGRP is the preferred route, and there's this administrative distance of 90. What we can do is we can create a static route, and we can have the static route entry pointing to the Miami path, the backup path. And what you do when you create this static route, let's say it's IP route 10, 10, 10, 0, 255, 255, 550, and then it points to the serial 010 interface. And then what you do is you set an administrative distance of like 91. Notice, because the administrative distance is higher, less preferred than the EIGRP, this static route won't be used unless the EIGRP route goes away. So the floating static route has an administrative distance that is intentionally set higher than the administrative distance of the preferred route. This keeps this particular route from being used unless there's a loss of the primary route. So a floating static route is a nice little redundancy trick commonly seen in wide area networking environments to provide that level of redundancy. Something else that we'll examine in this course is ether channel. Ether channel is a great layer 2 or layer 3 bundling or channel aggregation technology that you can use between your switches. We can have links between the switches. Let's draw 3 more links between these switches. And those can be bundled together with Ether channel, and that can all be made to look like one link. This is important for spanning tree protocol because if all of the links look like one link, then spanning tree protocol will not loop avoid that situation. Spanning tree protocol will not engage in its loop avoidance, and it won't shut down one of those links. So those links can be dynamically load balanced across without spanning tree protocol interfering with that situation whatsoever. So Ether channel is a great layer 2 or layer 3 technology that we can run for links between our Cisco Catalyst switches. And that makes our next slide a little easy for you. But by way of review for this lesson on high availability, I ask you what layer 2 or layer 3 channel aggregation technology allows you to bundle switch links together for load balancing and availability. And of course, the answer is Ether channel. But this reminds me to tell you about another channeling technology. That one, Ether channel, we're going to see in the LAN typically because we are bundling together links between switches. But let me tell you about another technology that we might see in the wide area network. In the wide area network, there is a bundling technology for multiple WAN links, and it's called Multilink II. So that's another channel aggregation technology where multiple links are bundled together by the point-to-point protocol to look like one link. So when we're talking about our switches and LAN-based technologies, we're traditionally talking about Ether channel, but when we're talking about bundling together WAN links, we're typically talking about the Multilink point-to-point protocol. So we took a look at important redundancy issues, redundancy technologies that we might see across any network model that we design. And coming up next, we'll take a look at technologies that we would design into any of our network designs for network management. Hugely important that we study network management technologies as designers so we can properly apply that important part of operating the network for the network operators. You want to build a network that is easily managed for the people that have to operate the network.